MiroCBT Management has developed and patented advanced processes for producing amino acid chelated minerals and selenium-enriched yeast. These innovations reflect MiroCBT's commitment to advancing high-quality, bioavailable supplements that support health and wellness. Amino acid chelated minerals. Minerals are vital for the proper functioning of living organisms. They serve as building materials for bones, influence muscle and nerve function, and are essential components of hormones and enzymes. Additionally, some minerals play a crucial role in the optimal functioning of the immune system. A deficiency in these minerals can increase susceptibility to infections and contribute to the development of chronic diseases. All necessary quantities of minerals are ideally obtained through the food chain. However, the repeated use of the same soils in agriculture, without balanced mineral replenishment, has led to a growing number of individuals being at risk of mineral deficiency. To address this imbalance, mineral food additives are commonly used. As Mr. Fletcher stated in the article Modern Miracle Men, presented to the Senate in 1936, the alarming fact is that foods, fruits, vegetables, and grains, now being raised on millions of acres of land that no longer contain needed minerals are starving us, no matter how much of them we eat. The bioavailability of mineral supplements. The bioavailability of mineral supplements depends on their form. In the early 20th century, dietary supplements primarily consisted of mineral supplements in the form of inorganic mineral bases, such as oxides and inorganic salts. However, subsequent studies revealed their low bioavailability. Later, it was established that the maximum bioavailability of minerals is achieved in the form of their chelates with amino acids. In the 1980s and 1990s, research proved that the bioavailability of some minerals in inorganic form can be less than 1%, whereas amino acid chelated minerals can reach bioavailability levels of up to 95 to 98%. Gradually, metals in the form of amino acid chelates began to replace their inorganic counterparts, partly due to restrictions on certain inorganic forms. For example, a ban on the use of zinc oxide for weaning pigs in the European Union came into effect in June 2022. However, in Canada, zinc oxide remains a primary ingredient for zinc supplementation in various nutritional products for both children and adults. Particular attention was given to zinc intake in the early stage of the COVID-19 pandemic, when the EVMS COVID-19 Intensive Care Protocol of March 31, 2020, emphasized the importance of zinc intake in chelated form for disease prevention, mildly symptomatic patients, and patients with respiratory symptoms. Subsequent research indicates that low zinc levels can impair the immune response to COVID-19 vaccination, even post-vaccination. An analysis of over 1,200 articles by the College of Allopathic Medicine, USA, and the Department of Internal Medicine at University Health Care, Hialeah, USA, found that zinc treatment was associated with reduced mortality rates. To this day, zinc supplementation remains important for those over 60, pregnant women, and individuals with medical comorbidities, due to the spread of new COVID variants, XEC and FLIRT. In 2011, the principal of MiroCBT patented a technology for producing pure amino acid chelated minerals for both humans and animals. During 2018 to 2019, pilot plant testing of this technology was conducted. The production line consisted of several key stages. 1. Water purification station. Tap water was brought to a suitable quality for the technological process using membrane filtration and reverse osmosis. 2. Synthesis. The synthesis of amino acid chelated minerals was performed in a reactor, following the patented process designed by the principal of MiroCBT. 3. Filtration and drying. After synthesis, the reaction mixture was filtered in the filtration unit and transferred to the spray dryer to obtain the product in powder form. 4. Granulation. Following the drying process, the powder should be sent to the fluid bed granulator to be transformed into granules. Powders can be challenging to handle in many industries due to their loose packing, lack of uniformity, and poor flowability during transport. Granulating the powder improves its density, flowability, and uniformity, making it easier to work with across various applications. Pilot plant testing, preliminary results. During pilot plant testing, amino acid chelate minerals were synthesized in a custom-designed 77-liter reactor. Following synthesis, the solution was filtered, and a control sample was spray-dried at the University of Alberta's Agri-Food Discovery Place. This process yielded 266 grams of solid material with a crystalline water content of 4.8%, derived from drying 1 liter of solution. Based on this outcome, the mass of amino acid chelated mineral in the powder was calculated at 253 grams, theoretically comprising 48.3 grams of zinc, 97.5 grams of aspartate, and 107.2 grams of lysine. Analytical testing for metal concentration was performed by SGS using the ICP-MS method, while an SGS subcontractor measured the amino acid content of the chelated minerals. The zinc concentration in a twofold diluted sample averaged 45.4 grams per liter of solution, approximately 94% of the expected concentration based on the mass of the dried sample. However, the analysis of the undiluted sample showed a lower zinc concentration than the diluted sample, suggesting that dilution improved analytical accuracy. For amino acids, the final solution's aspartic acid concentration was found to be 22.5 grams per liter of solution, or 23.1% of the expected value based on the dried sample's mass. Lysine concentration measured 30.4 grams per liter, representing 28.4% of the expected amount. According to SGS, the total dried chelated mineral mass was expected to be 98 grams per liter of solution, in contrast to the 253 grams per liter indicated by dried sample data. During analysis, hydrolysis was used for amino acid chelate measurement, but, as with protein hydrolysis, this process may cause amino acid loss. Unaccounted loss can lead to underestimation, likely affecting final product analysis. The yield of zinc and amino acid chelates in the 77-liter reactor was 82% of the theoretical yield, lower than the 96% yield obtained in laboratory experiments, likely due to differences in experimental conditions. The patented synthesis technology for chelated minerals requires simultaneous heating and stirring, which was feasible in lab tests. To replicate these conditions in the pilot plant, the 77-liter reactor was constructed. However, Hull Electric Limited installed a 30-amp cable and switch on the panel, while the mixer specifications required a 50-amp input switch. During the court hearing, case number 21599630, Hull Electric Limited v. MiroCBT Limited, Hull Electric testified that the actual power required by equipment can vary based on operational dynamics, including components functioning at different times, and that in some cases, a lower-rated cable and breaker could be adequate. In paragraph 144 of the judgment, Judge Malfair concluded that the work was appropriately executed and no deficiency discount was warranted. Due to this setup, heating and stirring were applied intermittently in the 77-liter reactor, deviating from the standard continuous synthesis process for chelated minerals. Without on-site analytical equipment, reaction duration was estimated based on laboratory protocols. Work plan for continuing pilot plant testing. 1. Electrical feed setup. Perform electrical setup for all equipment according to their technical specifications to prepare for synthesis operations based on patented amino acid chelated mineral production technology. 2. Synthesis parameters adjustment. Adjust synthesis parameters for producing amino acid chelated minerals in the 77-liter pilot plant reactor to match the yield obtained in laboratory conditions using a 1-liter reactor. This step ensures scalability to industrial production. 3. Optimization of drying process. Optimize the concentration of the amino acid mineral solution by pre-evaporating water to speed up the drying process. This should reduce evaporation time without increasing the solution's viscosity to the point where it cannot be pumped through pipelines from the concentration apparatus to the spray drying apparatus. 4. Granulation optimization. optimize the granulation of the chelated mineral powder obtained via spray drying. The following equipment is essential for monitoring production and testing the final product. Agilent 7800 ICP-MS system, for determining metal concentrations in the feedstock, during synthesis, and in the final product. Agilent 1262 HPLC for amino acid analysis, to assess amino acid purity in the feedstock and measure their concentration in the final product. Flash Smart NC Analyzer, to measure carbon and nitrogen concentrations in amino acids in the feedstock, during synthesis, and in the final product. Compact FTR Tensor 2 system, to measure the degree of chelation in the final product. Industrial process flow chart. After purification through the reverse osmosis system, 1. Tap water is added to the reaction vessel along with the metal hydroxide or carbonate. To initiate the synthesis, the reaction mixture is heated to the required temperature using steam, which is introduced into the reactor jacket. 2. Throughout the process, the temperature and mixing conditions are carefully maintained. The progress of the synthesis is monitored by measuring the ratio of metal, nitrogen, and carbon concentrations in the solution, which, by the end of the synthesis, must match their ratio in the chelate. Once the synthesis is complete, the reaction mixture is cooled using water circulated through a built-in spiral coil heat exchanger within the reactor. 2. The cooled reaction solution is then transferred to a filtration unit. 6. Where any unreacted solid particles are separated from the chelated mineral solution. The filtered chelate solution is concentrated in an evaporator. 8. Before being sent to a spray dryer. 9. The resulting chelated mineral powder is then processed in a fluidized bed granulator. 10. Producing amino acid chelated mineral granules of the specified size. Our company has not yet advertised its products but has already received a request for the supply of amino acid chelated minerals and selenium-enriched yeast. The production capacity of our pilot line for amino acid chelated minerals is currently limited to 10 kilograms of dry product per 8-hour shift, or approximately 750 kilograms per month if operating 3 shifts daily. Although the chemical reactor, with a 77-liter capacity, can produce about 21.5 kilograms of chelated minerals in solution per cycle, and we concentrate the solution twofold before spray drying, we are still limited to a maximum output of 1.5 tons of chelated minerals per month. Unfortunately, this capacity is insufficient to meet the demand of even a single potential client. Additionally, we hold a patented technology for producing selenium-enriched yeast, which can achieve selenium content levels of up to 5,000 ppm. These levels have been independently verified by analyses conducted in Canada, Tech Cominco, Global Discovery Laboratory, and the USA, PAR Laboratories Inc. Our company is the only one in the world with a patented technology for producing selenium-enriched yeast with such a high selenium concentration. The advantage of using selenium-enriched yeast as a dietary supplement, compared to inorganic selenium, which is toxic to living organisms, is that the main component of selenium-enriched yeast is selenomethionine, a natural amino acid that serves as a key endogenous antioxidant in many organisms, including humans. Thank you for watching. If this presentation has caught your interest and you would like to invest in promoting our products in the market, we would be happy to provide you with additional information. Please feel free to contact us.